Hi, I'm Jona Motta and I finished my PhD at the Laboratoire La Prince-Languet in Paris, and now I am a postdoc at UZH.
I'm Christopher Brown and I did my PhD at Imperial College London.
Hello, Namaskar. My name is Spandan Mondal and I received my PhD from RWTH Aachen University in Germany.
Growing up, I always liked physics and science, but I think I only really started liking particle physics when I did my undergrad. I'd really loved just the interesting maths and then the use of computation to solve problems, and I think particle physics was a good pairing of both of them. A few good supervisors later, and here I am.
I've always been interested in understanding the fundamental processes that govern our universe, and in parallel, I've also been interested in programming and automation. So experimental particle physics was pretty much the perfect fit for me.
What inspired me to be a particle physicist is mainly my curiosity for how things work. When I was little, I just liked to break stuff apart and understand what were the pieces that make it work. And particle physics is a way of understanding how the universe works by studying the fundamental particles and fundamental forces that regulate them. So yeah, I guess that.
I would say prioritize your mental health and find ways to do what makes you happy. So for example, if staying home makes you happy, then find ways to work from home.
Ask more questions, because when one starts a PhD, generally you're a bit shy and you think like, oh, if I ask a question, then someone will think I'm stupid.
I think if there's anything I was confused about, anything I wanted to know, anything I was just interested in, I think just asking questions of my supervisors, other postdocs, other PhD students as well. I think they'll always be happy to help and probably interested in the problem you want to solve as well.
And you will always learn much more than you expect just from the question.
I think I'll go big and say, why did the Big Bang happen? I think that would be a cool thing to know, and it's the reason why all the other particles exist and why we exist, to ask that question.
We'll go for trying to understand if our theories are actually what the universe works on, in the sense that, for example, the standard model, all the forces arise from symmetries, from geometrical symmetries of the theory. So the question is, does the universe actually know about these geometrical symmetries, or is just our way of understanding it, and it's just sort of anthropomorphizing the universe so that we can understand it?
I would like to know what kind of particles dark matter is composed of. We have several theories that propose different dark matter candidates, and I would like to know which of these, or if any of these, is true.
So the focal point of my thesis was the study of Higgs boson pair production, which allows us to study one specific property of the Higgs boson, which is fundamentally correlated with many questions that we have about the universe. One is the stability of the universe, and one is why is it so full of matter and not of antimatter. In order to do this kind of analysis, we need to take data from the LHC, from our proton-proton collisions, and the LHC gives us much more data that we can actually store. So we have some triggers, we call them triggers, to select the specific events that are most interesting. I was lucky enough to work on the level 1 trigger, developing machine learning techniques to be implemented in hardware for the selection of the tau leptons.
My thesis involved searching for the Higgs boson decaying into charm quarks. It's a particularly interesting process because its rate can be significantly altered by the presence of new physics. At the same time, it's particularly challenging because the process is extremely rare, and identifying jets arising from charm quarks is also particularly difficult. So the first part of the thesis was to improve this charm identification part. I developed a new calibration method that allows us to maximally leverage the outputs obtained from machine learning-based jet taggers. And this new method allows us to improve sensitivities of searches involving charm quarks. And then the next part of my thesis was focused on performing the Higgs search. And combined with other results, we were able to set the most stringent direct upper limits to the Higgs to CC process to date. In parallel, we validated this analysis by searching for charm decays of the Z boson and the W boson. And in this parallel effort, we were able to make the first observation of charm decays of the Z boson at a hadron collider experiment, and also the first standalone observation of charmed decays of the W boson at a hadron collider.
So my PhD was working on the upgrade to CMS, so looking at how we select events for the high luminosity LHC. I worked on integrating machine learning algorithms into our trigger. So I first looked at using a precision tree to evaluate tracks coming from our track finder. And then I also looked at using a convolutional neural network to find the primary vertex in event, and that allows us to filter out some of the background coming from overlapping proton-proton collisions that happen in every single LHC bunch crossing. The final part of my PhD was working on sort of asking what happens when we put this kind of machine learning of our trigger into a evolving system. So CMS and the LHC are not static, and they're continually updating. So we should also look to update and change our machine learning as we go as well. And I implemented a continual learning approach to this, where you incrementally update your machine learning to be as efficient and as productive as possible as the changing conditions evolve.